We're continuing our discussion of Bohr's correspondence principle. In part A, we found that the frequency of the nth orbit is given by this expression. Part B, in classical physics, the frequency of revolution of the electron is equal to the frequency of the radiation that it emits. Show that when n is very large, the frequency of revolution does indeed equal the radiated frequency for a transition from n1 equals n plus 1 to n2 equals n. This illustrates Bohr's correspondence principle, which is often used as a check on quantum calculations. When n is small, quantum physics gives results that are very different from those of classical physics. When n is large, the differences are not significant and the two methods then correspond. In fact, when Bohr first tackled the hydrogen atom problem, he sought to determine f as a function of n such that it would correspond to classical results for large n. Now, the energy of the electron in the nth quantum level will be given by the contribution E sub n is equal to kinetic energy contribution plus potential energy contribution. What's the kinetic energy? It is 1 over 2 m v sub n squared, and the potential energy minus 1 over 4 pi epsilon 0 E squared divided by Rn. That's the electric potential. Okay, and potential energy. Now we can divide and multiply by R sub n for the first term. So we will have 1 over 2 m Vn square R sub n divided by R sub n, the kinetic energy, minus 1 over 4 pi epsilon 0 E squared over R sub n for the potential energy. And this is equal to, so we have mv square over r is equal to the centripetal force. So we have r sub n divided by 2, 1 over 4 pi epsilon 0, the centripetal force. So this is our centripetal force here, mv squared over r, E squared divided by R sub n squared. So you can see that the R sub n's will cancel, and the second term is minus 1 over 4 pi epsilon 0 E squared over Rn. And this will give us, it's the same term here, half of it. So you can see this will give us minus 1 over 8 pi epsilon 0 E squared over R sub n. Okay, so it's the potential energy divided by 2. That's basically what we're finding for the final total energy of the system. So E sub n is equal to minus E squared over 8 pi epsilon 0. And for 1 over Rn, we're going to substitute the result we found in part A, 4 pi epsilon 0 over me square n square h bar square. So this will give us me square divided by 4 pi epsilon 0 n square h bar square. So we have substituted for 1 over Rn here. And this will give us minus me to the fourth power divided by epsilon 0 square, and we have h bar square is h square divided by 4 pi square, and then we have 8 times 4 pi square, and then we have 1 over n square. So here epsilon 0 square, h bar square is h square over 4 pi square, 1 over n square is here, and here I have epsilon 0 square, 8 pi times 4 pi is 8 times 4 pi square. So you can see that these 4 pi squares will cancel out, and I will be left with minus me to the fourth power divided by 8 epsilon 0 square h square times 1 over n square. So that's the total energy. Now we can find the transition from n equals the n plus 1th level to nth level, En plus 1 minus En. That's the energy difference between these two levels. That is minus me to the fourth power divided by 8 epsilon 0 square h square, and we will have 1 over n plus 1 square minus 1 over n square. Okay, and for the term 1 over n plus 1 square minus 1 over n square, when n is much greater than 1, we're looking at the classical limit here, 1 over n plus 1 squared minus 1 over n squared is equal to n squared minus n plus 1 parentheses squared divided by n squared n plus 1 parentheses squared. And let's see what that will simplify to. So we will see that 1 over n plus 1 squared minus 1 over n squared is equal to n squared minus n squared minus 2n minus 1 divided by n squared times n plus 1 squared. These n squareds will cancel. And since n is much greater than 1, this 1 will be neglected as well. So we can say this is approximately minus 2n divided by n to the fourth power. Why? Because this 1 can be neglected compared to n as well. So this can be written as minus 2 divided by n cubed for n much greater than 1, and 2n is also much greater than 1. Okay, so the energy difference between the two levels, delta E, which goes to the radiated emitted radiation, is approximately minus me to the fourth power divided by 8 epsilon 0 square h square multiplied by minus 2 over n cubed. And this will give us e to the fourth power divided by 4 epsilon 0 square h square n cube, because you see that this 2 will make this 8, 4. And what is this? Me to the fourth power multiplied by 4e0 square h square n cube. This will be equal to the energy of the radiated photon, which is h times frequency energy of the photon. So what is the frequency of the emitted photon? It is me to the fourth power divided by 4 epsilon 0 square n cube h cube, which is identical to the answer we found in part A. So we find that the frequency of the emitted radiation corresponding to the energy difference between the two levels for the relaxation of the electron is equal to the frequency of the revolution of the electron around the nucleus. And for which n values is this correct? For large n values. The classical result is reproduced. So Bohr's correspondence principle applies. So what we have done here is we have written the total energy of the electron, kinetic term 1/2 mvn square, potential energy term minus 1 over 4 pi epsilon 0 e square over r, and we multiply top and bottom with r. We recognize mv square over r as the centripetal force, and this allowed us to write the total energy in this form. Well, for r sub n, we found in part A, it is given by 4 pi epsilon 0 over me square n square h bar square, so that's substituted here. So we can calculate the energy levels as a function of n with this final result. For a transition from n to n plus 1 or n plus 1 to n, the energy difference n plus 1 minus n energy difference is this, where we encounter the term 1 over n plus 1 parentheses square minus 1 over n square, and when n is much greater than 1, that term we have shown to be equivalent to minus 2 over n cube approximately. Substituting this result to delta E for this term, we obtain the energy difference between the two levels, which should correspond to the energy of the emitted photon, emitted radiation, h times f, and that gives us the frequency of the emitted photon to be equal to the frequency of revolution of the electron around the nucleus, which is true for large values of n. So Bohr's correspondence principle works.